Hello everyone. We're from Group 5, and today we're gonna present about gravitation. My name is Arkindra.
My name is Indira Raeesha.
And my name is Azka Tsaniya.
Okay, first of all, we're gonna talk about Newton's law of gravitation. So the gravitational force is responsible for a lot of things. It's hold us to the Earth, hold Earth in orbit around the Sun, holds the Sun together with the stars in our galaxy, reaches out across intergalactic space to hold together the local group of galaxies, hold together the local supercluster of galaxies, pulls the supercluster toward the great attractor, attempts to slow the expansion of the universe, and is responsible for black holes. Uh, and gravity is far-reaching and very important. Uh, Gravitational attraction depends on the amount of stuff an object is made of. And because Earth has a lot of stuff, it is produce a large attraction. The force is always attractive; it never repulsive, and the gravitation is the tendency for bodies to attract each other. Newton realized this attraction was responsible for maintaining the orbits of celestial bodies. And Newton's law of gravitation defines the strength of this attractive force between particles. And for example, for Apple and Earth, they have zero point 0.8 Newton, and for two people, they have less than 1 micronewton. Next. So we have this formula. The magnitude of the force is given by, we can use this formula to search the force. And where G is the gravitational constant, 6.67 times 10 powered by -11. The force always point from one particle to the another. So this equation can be written in vector form by changing the function to vector 2. Next. So describe gravitational attraction for object. A uniform spherical shell of matter attracts a particle that is outside the shell, as if all the shell's mass were concentrated at its center. Earth is a nesting of shells, so we feel Earth mass as if it were all located at its center. Gravitational force forms the third law force pairs. For example, like Earth and Apple Earth forces are both 0.8 Newton. Next. So because of the difference in mass between Apple and Earth, it causes the difference in the Apple and Earth acceleration. Uh, it is 10 meter per second square versus 10 to the power minus 25 meter per second square. Next. Uh, okay, so now it's time to talk about gravitation and the principle of superposition. First of all, find the net gravitational force by the principle of superposition. The net is the sum of individual effects. At the individual forces as vectors, and for a real extended object, this becomes an integral. If the object is a uniform sphere or shell, we can treat its mass as being at its center instead. Next. So this is if we have object in, you can look at the A. If we have some object in M1, M2, and M3, we can search the gravitational force in M1 just by adding the gravitational force in M2 and M3. Next. Okay, so let's solve some problems. In this figure, a square of edge length 20 centimeter is formed by four spheres of masses. M1 have 5 gram, M2 3 grams, M3 1 grams, and M4 5 grams. In unit vector notation, what is the net gravitational force from them on a central sphere with mass M5, 2.5 gram? Feel free to pause and uh, s- find the solution. So, okay, next. So this is the solution. The gravitational force on M5 from the two 5 gram masses M1 and M4 cancel each other. Contribution to the net force on M5 come from the remaining two masses. So Fnet, we search Fnet uh, by this equation, and it's has an answer 1.67 times 10 to the power minus 14 Newton. And the force is directed along the diagonal between M2 and M3 toward M2 in a unit vector notation we have. Next.
Okay, so now I'm going to discuss about gravitation near Earth surfaces. Uh, from this formula, we can get the gravitation acceleration by combining the Newton laws of gravitation and Newton's second law. This gives the magnitude of the gravitational acceleration at a given distance from the center of the Earth. And the table shows the value for gravitational acceleration for various at altitudes above the Earth's surface. Next. The calculated acceleration will differ slightly from the measured g at any location. Therefore, the calculated gravitational force on an object will not match its weight for the same three reasons. First, Earth mass is not uniformly distributed, and second, Earth is not a sphere, and third, Earth rotates. Next. For example, difference in gravitational force and weight due to rotation at the equator, and this is the formula. Next. And gravitation inside Earth. From the theorem, we know that a uniform shell of matter exerts no net gravitational force on a particle located inside. Forces between elements do not disappear, but their vector sum is zero. Now let's find the gravitational force inside a uniform density Earth, where Earth is a solid sphere and not a shell. Next. Um, Now we substitute the constant density into the equation, and then we write this as a vector equation by substituting k for the constant. And when object drop through Earth, it oscillates due to Hooke's law. Next. And gravitational potential energy is a property of a pair of particles, and we cannot divide it up to say how much of it belongs to each particle in the pair. And we often speak as of the gravitational potential energy of a ball in the ball Earth system, and we get away with this because the energy change appears almost entirely as kinetic energy of the ball, and this is only true for a system where one object is much less massive than the other. Next. Gravitational potential energy for a two-particle system is written as this formula. Note this value is negative and approaches zero for r to infinite. And the gravitational potential energy of a system is the sum of potential energy of all pairs of particles. Next. The gravitational force is conservative, and the work done by this force doesn't depend on the path followed by the particles, only the difference in the initial and final position of the particles. Since the work done is independent of path, so is the gravitational potential energy change. Next. Newton's law of gravitation can be derived from the potential energy formula by taking the derivative. For a projectile to escape the gravitational pull of a body, it must come to rest only at infinity. If at all, k equal to 0 and u equal to 0 because r is infinite. So k plus u must be at least 0 at the surface of the body. That's why rockets launch eastward to take advantage of Earth's rotational speed to reach the V more easily. Next, and this is some escape speeds from Ceres, Earth, Moon, Earth, Jupiter, Sun, Sirius, and neutron star. Next.
Okay. The next one we will discuss about is planet and satellites, and Kepler's law. The motion of planets in the solar system was a puzzle for all astronomers. In the history, there are two models of universe. The first one is geocentric theory and heliocentric theory. The geocentric model says that the Earth is at the center of the cosmos or universe, and the planet, the sun, and the moon and the stars circles around it. And the heliocentric models consider the sun as the center and the planet revolve around the sun. So Johannes Kepler here is the one that validates, the one that justifies about the heliocentric theory, which results in the Kepler's law. Okay, so now we discuss about the Kepler's law. The first law is the law of orbits. All planets move in elliptical orbits with the sun at one focus. The orbit here is defined by its semi-major axis A and its eccentricity or E. An eccentricity of 0 corresponding to a circle. The eccentricity, the greater than 0, less than 1, will equal to the ellipse eccentricity. And the eccentricity of Earth itself is 0.0167. The second is the law of area. A line that connects a planet to the sun sweeps out equal areas in the plane of the planet orbits in equal time interval. So if you can see here, the area in C to D is the same as the area in A to B. It's also the same as the time consumed from A to B, and the time from C to D. The third law is the law of periods. The square of the period of any planet is proportional to the cube of semi-major axis of its orbit. The law of period can be written mathematically as this equation. This is also holds for elliptical orbits if we replace r with a. Okay. The next one, relating the centripetal acceleration of a satellite to the gravitational force, we can rewrite as energies. This is the equation of kinetic energy, meaning that the k are equal to u per minus u per 2 in circular orbit. Therefore, the total mechanical energy we can mathematically written as this. Okay, next. Satellites, orbits, and energies. Total energy is the negative of the kinetic energy. For an ellipse, we substitute A for R. Therefore, the energy of an orbit depends only on its semi-major axis, not its eccentricity. All orbits in this figure have the same energy, even though the eccentricity is different, but because we depends only on the semi-major axis, so we can conclude that all orbits in here are the same energy. Okay, now we discuss about Einstein and gravitation. The general theory of relativity describes gravitation. Its fundamental postulate is the principle of equivalence. Gravitation and acceleration are equivalent. So in this picture, the experimenter inside this box is unable to tell whether he is on Earth or he is on free space. On the A side, he is on Earth experiencing gravitation equals to 9.8 meter per second square, or in free space, he experiencing acceleration at 6.8 meter per second square. Okay. In this theory, we can tell that space or space-time is curved. If we talk in analogies, in this picture, in A and B, paths that appear to be parallel along the surface of the Earth or falling toward the Earth center actually converge. We can see why by stepping outside the curved Earth, but we can step outside of curved space. But we can observe the curvature of space. Light bends as it passes by massive objects, an effect called gravitational lensing. In extreme cases, we observe the light coming from multiple places or bend into an Einstein ring, as it's shown in the photo. Okay, last. However, the source of gravitation is still unclear. Is it purely an effect of curved space-time, or is it a force between the masses, or is it due to the fundamental particle degravitation, which would carry gravitational force? Yet all of these questions are not settled until now. Okay, I think that's it from us. Thank you for listening. Assalamualaikum warahmatullahi wabarakatuh.